record. Okay, for this problem, we will approximate the first and second derivative of this function. The first and second derivative of this function, we have the function, the polynomial function, right? And as it's very easy to determine the exact one, the exact solution. Okay, so we have to compute the exact solution, and then we have to determine the percent relative error for this approximation. Okay, so for this case, we would like to approximate by using central difference, because this is the best one. It is the best one because of we have the function. Okay, so when we would like to approximate the derivative, okay, central difference is very good for that case. Okay, so let me start. Okay, so this is problem number 2, right? Okay, for problem number 2, okay, we may have to use the central difference formula. Okay, for the central difference, we have the central difference formula is something like this. Okay, that is for the error, the truncation error of order s square, right? And if we would like to use the more accurate formula, okay, for more accuracy, that's we have the formula is something like this. It's the more accuracy. So then for this problem, actually the problem is not given that what the accuracy that the problem would like to have. So then we will determine both. For the normal accuracies, that is the error of order s square, and also for the accurate more accurate formula, that is the error order of s power 4. Okay, so we may have to starting with determine the exact solution first. So who can help me to determine the exact solution, please? Okay, from this problem. From this problem, that's we have the function of like this. This is a polynomial of order of the degree of 7 degree. Okay, so we have a equal to kn, right? Sorry. Kn, p number is what? I don't know. For this case, I may starting with this. Maybe for example, it's maybe for someone number something. Okay, so then a is maybe equal to kn times 10 power minus 4, right? Okay, we have a already, right? Okay, so what's next that we should do now? Okay, so if we would like to determine the exact solution, okay, so we have to take the first derivative of this. We would like to determine the first and second derivative, right? First and second derivative. Okay, so then what is the first derivative of this function? F prime x is equal to what? F prime x is what?
Uh, 7ax power by 6.
Power 6. Okay, that's right.
Yes,
thank you.
and
okay.
Minus 15x power 4.
Then
minus 42x square. I mean, yeah.
Okay.
Power by 2 and plus 3.
Plus 3. Then and then second derivative is become
42ax power 5
42x power 5 minus
minus 60x power 3
3x power 3 and then minus
minus 84x.
x, okay, and then that's all, right?
Yes, sir.
Okay, that's all. So
No,
then we
hello, for the first derivative, I think is 52a squared.
sorry.
For the first derivative, yeah,
What's the
yeah, there's 52a squared. That should be. No, not 42. It's 52.
So what's term?
Sorry. I my fault.
Okay, that's good. Thank you. Okay, so then we need to determine 7a and 42a, right? Okay, so then in order to determine the exact solution, right? Okay, so we may determine 7a and 42a for the case that we would like to change a, right? Okay, so then 7a is become what? Sorry. Please wait a minute. I think my internet is maybe okay. Then we have 7a, right?
อาจารย์ไม่ได้พอร์ตเหรอครับ
I just resume it. Okay. And 42 times a. It is for the case that we would like to change value of a for this case. And then we may determine the exact solution first. For this time, we have the value for determining that. Okay, for the exact solution. Exact solution is what? So for this case, dy by dx, okay, is equal to what? And then the dy by dx2, okay. And this may be for the case that we type in coding language, okay, we may use the symbol like that. Okay, but if you writing in the report or something, is maybe not necessary, not we not use like this. Okay, we use another thing. Okay, for dy dx is equal to what? Is equal to 7a, right? Oh, sorry. We have to determine x. So x is what? In this case, x is now for this problem x is equal to 1, right? Okay, so dy dx is become 7a times x power 6. Okay, x power 6 minus 3 times x. Sorry, I use the formula. I use the wrong formula. 7a x power 6. That's all right. But minus what? 7a times x power 6. That's correct. Minus 15, right? Minus 15 times x power 4. Okay. So please help me because my brain has burned in the morning and I may have a lot of error today. Okay, so 44 times x power 2, okay, and plus 3. Okay, so then am I correct? That should
Yes.
be all right. Okay, so then the second derivative is become 42a, right?
Yes, sir. 42a.
X power 5. Okay, and minus 60, right? x power 3, okay, minus 84x. Okay, we have the exact solution already, right? Okay, we already have exact solution. That's maybe first problem. Okay, then if we would like to determine the central difference, okay, for the first derivative and second derivative, if we would like to use the more accurate, for this case, the more accurate formula for the second derivative, we require until x plus 2 and x minus 2, right? X plus 2 and x minus 2 for second derivative. Okay, so then we have to prepare our data first. Okay, until x plus 2 and x minus 2. Okay, the value of x should be xi, right? Okay, xi is equal to what? Xi is equal to x. Okay, and we have xi minus 1, right? Okay, xi minus 1 is equal to what? It's equal to, sorry, we forgot something, right? We forgot what? We forgot h. Okay, so then s is equal to what? S is equal to 0.1 for this case. Okay. S is equal to 0.1. And it should be xi minus 1, right? Okay, and it should be xi minus 2. Okay. So xi minus 1 is equal to what? Is equal to xi minus h. Okay, and it should be xi minus h. Okay, and xi plus 1, right? And this is xi plus 2. Okay, it should be xi plus h and xi plus 2h. Okay, it should be all right. Okay, it should be all right. Okay, after we have fx already, right? Then we determine for fx. Okay, fx should be okay for fx. Fx is equal to what? Okay, fx is equal to a. Okay. Times x. Okay, power 7 minus 3 times x power 5. Okay, minus 14 times x over 3. Okay, plus 3 times x. Okay, minus 2, right? Okay, am I correct? Should be all right. Okay, and then it should be like this. Now we have fx already, right? Okay, so then we may determine for the central difference. We may starting with OH2 first. So for the case that central difference with OH2, okay. So this is about the percent error, right? And this is we would like to determine dy dx and d2y dx2 for the case of central difference with order of OS square, right? Okay, for this case first, so the formula is what? The formula is fxi plus 1 minus fxi divided by 2h. fxi plus 1 minus fxi minus 1. Okay, divided by 2h. Okay, so we have the solution like this. Okay, that's for the case that we use s equal to 0.1. Okay, and the error is what? Error is in comparison with the exact solution, right? Okay, we have 1.653%. Okay, and then for d2y dx2 is equal to what for this case? For d2y by dx2 is fxi plus 1, right? fxi plus 1. Okay, minus 2 fxi. Okay, plus fxi minus 1. You're right, and divided by x squared. Okay, it should be, we have value like this. And the percent error is about okay, we have the percent error of 3.545, sorry, 3.537%. Okay, this is for the case that we use the central difference of the OS square, right? And if we use the high accuracy, if you use high accuracy, so what's that? Do the same thing, right? And dy dx is become, for high accuracy, we have to use these. Okay, for high accuracy is what? It's equal to minus fx plus 2, right? Plus 8 fx plus 1. Okay, minus 8 fx minus 1. Okay, plus fx minus 2. Okay, and then divided by 12h. Okay, so then we have solution like this. Okay, okay, the percent error is reduced when we apply the high accuracy formula. Okay, and for the second derivative equal to minus fxi plus 2 plus 16 times fxi plus 1 minus 30 times fxi plus 16 times fxi minus 1 minus fxi minus 2. Okay, divided by 12 times h squared. Okay, we have value like this. Okay, it means the percent error. Okay, so then you see that for this problem with h equal to 0.1, okay, if we use the formula of OS square, see that the error is around 1.16% for first derivative and 3% for second derivative. Okay, but if we increase the accuracy by using more accuracy formula, okay, we found that the solution is better. Okay, the solution is better, is the error is reduced in comparison with the exact solution. Okay, so but you see that the error for this case, for the case of the general formula, that is OS square. Okay, when we change the more accurate to be OS, also the error is not depend on the size. Okay, for this case, it's not the ratio for the result of the error. Okay, because it's the high, it's more accurate. Okay, but if we change the size of h, okay, so if we remember like this, okay, if we change the size to be, the size is maybe 0.05, for example, we reduce it to 1/2. Okay, so then the percent errors may be reduced. That is depend on the size h. Okay, that we have discussed last time. That is it depends. Okay, it depends on the formula that we apply. If it's OS square, so the error is maybe reduced, maybe 1/4 or 1/4 of the size that we reduced for 1/2. Okay. Okay, then for this problem, it should be all right. Okay, so then we may move to next problem. Okay, to next problem. What's that? We have discussed this problem before we end of the class last time. Okay, so then for today we will working with this. That is very easy to work out. Sorry, I clock the problem first. Okay, for the second problem, that is something like this. We may have to create the table first. Okay, it's maybe like this. Key number is okay. So the table for this problem, we may create the table for this problem like this. As we have time, right? Okay, and Y. Okay, and this is equal to Kn in minus 3, right? Okay, it's become 50 and it is 68. Okay, so for velocity, velocity is what? Velocity is the first derivative of the function y, right? And acceleration is the second derivative of function y. Okay, so then we will use the central difference. Okay, so for the middle data, we will use the central difference with of order s square. Okay, we use central difference for order s square, and after that we will apply the more accurate forward difference and more accurate backward difference for the both end. Okay, we may starting with the central difference. That's very easy to find. This is the formula for central difference of order s square. Okay, so for the middle data, can we use the central difference? That is what? It is fxi plus 1, right? Fxi plus 1 minus fxi minus 1, right? Okay, divided by 2h. Okay, on this case, h is what? I forgot. Okay, so h for this case, because this is equivalent, it's become okay, this is become 2 seconds, right? And for the first derivative, it's become fxi plus 1 minus fxi minus 1, right? For the middle data, we have the forward data and backward data. That's okay, that's fine. Can determine by using the central difference h. Okay. Okay, we already have the velocity, right? And after that, for another value, that's just we may have the same formula, right? And for the second derivative, it's equal to what? It's equal to fxi plus 1, right? Minus 2 times fxi, okay, plus fxi minus 1, okay, divided by s squared. Okay, right? Okay, we already have the velocity and acceleration rate like now. And for the first data and the final data. That is for the first one, we do not have the data previous this one. Okay, so we cannot apply central difference and backward difference. So we should apply the forward difference with high accuracy. That is the error of the same order of central difference. That is the error of order S square, right? Okay, in order to use the error in the same order, okay, this error of S square is the same as the central difference like this. Okay, so yes, we have to use more accurate formula for forward and backward difference. So for forward difference, that is a first derivative. It's equal to what? It's equal to minus fxi plus 2, then it should be here, plus 4 times fxi plus 1, okay, minus 3 times fxi, okay, divided by 2h, okay, and for the acceleration is equal to second derivative, that is equal to minus fxi plus 3, right? It's 1, 2, 3, it should be here, okay, plus 4 times fxi plus 2, okay, minus 5 times fxi plus 1, okay, plus 2 times fxi, okay, very easy, right? And divided by h squared. As we already have, so something like this, okay, this for forward for the first data, okay, then for the case of final data, that is we have just only backward data, so we have to use backward difference. So for the case of the first derivative, it's become 3 times fxi, okay, minus 4 times fxi minus 1, okay, plus fxi minus 3, okay, divided by h squared. Okay, it's for the velocity at the endpoint. And for the acceleration, which is the second derivative, which is become 2 times fxi minus 5 times fxi minus 1 plus 4 times fxi minus 2 minus fxi minus 3. And divided by h squared. Okay, we have the data like this. Okay, that's all for this problem. Okay, are you okay for that? Easy, right?
โอเคครับผม
Okay, thank you very much for your response. That is very good for me. Okay, so I think it should be. I will stop the clip for this case, and then we will go to the final problem.